A circuit with two loops, as shown in the picture, is set up. The switch is open initially, and then we close the switch. What is the current in each branch right after the switch is closed? Let's start with the right-hand branch. We have an inductor on the right-hand branch, meaning the current on that branch cannot change immediately because it was 0 before the switch was closed. Right after the switch is closed, I3 will still be equal to 0. That's because of the inductor. Now let's apply the junction rule at point A to find the other two currents. According to the junction rule, current going into a junction has to be equal to the current going out of the junction. Into the junction we only have I1, and out of the junction we have I2 and I3, so I1 equals I2 plus I3. We have already determined that I3 is equal to 0, so I1 is equal to I2. So that's the same current on those two branches, I1, I2. So really the left-hand side branch at the very beginning, right after the switch is closed, we only have a single loop circuit, the very first moment that is. We only have a single loop circuit, which is the left-hand side loop of the circuit. It's as if the right-hand side is not there yet. We can apply the loop rule on the left-hand side loop. Starting from point A, we go clockwise. The first element that we see is R1, and we're going in the direction of the current. That's a drop in the voltage or a decrease in the voltage. That's minus R1 times I2, and then we cross the battery from its negative terminal towards its positive terminal. That is an increase in voltage. That's plus EMF. And that's it. So that's equal to 0. Rearranging our equation, we get I2 equals EMF divided by R1, and I1 is equal to I2, so I1 is also EMF divided by R1. What is the current in each branch a long time after the switch is closed? A long time after, the inductor will act like a short circuit. So the current on the inductor will start from 0, it'll grow, and then it'll reach a maximum value. It'll stop changing at that point. Because the current on the inductor stops changing, the voltage across the inductor will become equal to 0 because it's proportional to the rate of change of current. Because the rate of change of current will be 0 when the current reaches a steady state, the voltage across the inductor will become 0. So then V sub L is equal to 0 a long time after the switch is closed. Let's start with the left loop again, applying the loop rule. It's exactly the same equation. Negative R1 I2 plus EMF equals 0. So really there's no change in the middle branch, so I2 is still equal to EMF divided by R1. Now focusing on the big loop, again starting from point A going clockwise, we have negative R2 I3 and then nothing across the inductor, 0 potential difference, plus EMF is equal to 0. So then I3 is equal to EMF divided by R2. To calculate I1, we can apply the junction rule at point A, similar to what we did before. I1 is equal to I2 plus I3. This time I2 is the same, but I3 is different. I1 is then equal to EMF divided by R1 plus EMF divided by R2. At what time does current I3 reach half of its maximum value? Now, if you focus on the outer loop, it's really just a simple RL circuit. It consists of a battery and then one resistor and one inductor. Therefore, we can model I3 as the growing current in an RL circuit, and the formula for that is maximum current I sub M times 1 minus exponential of negative RT over L. Of course, R here is R2, the resistor that is connected next to the inductor L. Now we want the ratio I divided by IM to be equal to 1 over 2. meaning I will be equal to 1/2 of its maximum value. Let's divide both sides by I sub m first. Here I have divided both sides by I sub m and then substituted 1/2 for I divided by I sub m. Now let's rearrange our equation to isolate the exponential term. Here we have the exponential term isolated. Now to get rid of the exponential, let's take the natural log of both sides of the equation. After taking the natural log of both sides, we get rid of the exponential on the left hand side. So on the left we have minus r2 times t divided by L equal to ln of 1 minus 1/2, which is equal to 1/2 or 0.5. Multiplying both sides by negative L and divided by R2, we get t equals minus L/R2 times ln 0.5. Now you may think that there's a negative sign. Does that mean we get a negative value for time? It turns out, remember, we're calculating ln of 0.5, which is a negative value because 0.5 is less than 1. So the two negatives will cancel and the time value will be positive as expected. What is the current in each branch when I3 reaches half of its maximum value? Let's start with I3. We have already calculated its maximum value. Now its value will be just that divided by 2. The maximum value of I3 was EMF divided by R2. Half of that is EMF divided by 2 times R2. To find the current I2, again we can apply the loop rule on the left hand side loop. Starting from point A, going clockwise, we have the exact same equation, no change here. Minus R1 I2 plus EMF equals 0. So I2 is equal to EMF divided by R1. So note that I2 never changes from the beginning to the end. It always has the same value, which is EMF divided by R1. But as time goes by, I3 will grow from 0 and I1 will grow accordingly because I1 has to be equal to I2 plus I3. So now let's apply the junction rule again at point A to calculate I1. Here we have junction rule applied at point A. I1 equals I2 plus I3. Substituting the values from above, we get I1 equals EMF divided by R1 plus EMF divided by 2 times R2.